What do modern databases and Agent Smith have in common? Well, they both understand that one is not enough. Hi, I'm Ivan Fedyanin, and today we will learn basics of leader-follower replication. This video will introduce main concepts of this topic, and in the next videos we will be doing more deep dive into some specific topics. We start with the concept of the replication itself. In a nutshell, it means storing a single piece of data on multiple servers, often distributed among the world. This gives us multiple benefits. First one is scalability. When number of clients grows, we can simply increase number of servers. Performance. System works faster by spreading load across multiple replicas. Availability. When one replica fails, system can use others, so system remains available. Low latency. By placing data nearer to clients, we avoid network delays. And an extreme case of this is caching, when data are on the client side itself and client needs to make remote calls only in case of cache miss. Fault tolerance or reliability is very similar. When one replica fails, system continues functioning. And durability. When the data is written and acknowledged, even if a single server fails, the data are guaranteed to be not lost. And those are really impressive benefits. But what are the trade-off? And the trade-off here is consistency. Because when we have the same piece of data on multiple replicas, the question is how to keep them consistent, how to ensure that when we constantly update the data, they remain the same in every location. Those are serious questions, but luckily, extensive research has made its way into the industry, resulting in multiple techniques available for us to use. There are several ways to build a replication system that addresses those challenges, and today we will explore specifically one technique called leader and follower replication. This technique is probably the easiest for understanding. The main idea is that we have single node called leader or sometimes master primary, and this node accepts writes, the only one of all nodes. And we have multiple other nodes called followers, replicas, backups, or read replicas. And those nodes are designed only to serve reads. And leader node constantly streams replication data to follower nodes. Replication in general has two challenges. The first one is total order of all writes, and the second one is conflict resolution. And each technique of replication handles them differently. In leader-follower model, total ordering is achieved by having only a single node that accepts writes, and because of this, during the acknowledgement, it just orders them in some total way. And conflict resolution is not applicable to this schema because conflicts are simply avoided because we have only one leader node who accepts writes, so there are no possibility for conflicts. When client sends a write request to leader, leader is responsible to distribute it to all followers. And then for read queries, client can use either leader or followers. If client use leader, then we have strict consistency. And when client uses followers, because they lag behind, the consistency is not very strict, but it allows horizontal scaling for reads. So, as we can see, this method is very simple to understand and implement, and because of this, it was implemented in majority of well-known database products, which we all know. However, despite its seeming simplicity, this schema have quite a few ways of implementation and also has a lot of nuances. Probably the first question to ask when we consider a leader-follower system is to make it synchronous or asynchronous. When system works in synchronous mode, leader, when it receives the request, it must send it to every follower synchronously, and only after all followers will respond to it, it can acknowledge the request to client. As a result, each follower has exactly the same state as a leader at every moment. So if leader fails, no data will be lost. Also, in that mode, we have very strict consistency because if client reads data from follower, it can be sure that they would be exactly the same as if read would have happened from the leader. However, the trade-offs are performance and availability. So, because leader has to wait until every follower responds, the response time of the system would be equal to the response time of the slowest follower. Additionally, if at least one of synchronous followers will fail, then we will never be able to complete the write because leader would not be able to get a confirmation from that follower that the write was concluded. So, to mitigate drawbacks of synchronous replication, we could use asynchronous one. In that mode, leader will acknowledge client write immediately, and then it will asynchronously replicate the changes to followers. By this, we immediately solve performance problem because now the response time of the system will not depend on any follower. It will depend only on local processing on the leader. And also it will increase availability because if any number of followers fail, leader would be able to process the requests. The trade-offs here are consistency and durability. Because data are not replicated immediately, it's possible that leader receives request, acknowledges, and the client already thinks that the request was acknowledged, but after that leader could crash. And if the data were not yet replicated to any followers, data will be lost. And the second quite big problem is consistency. Because of asynchronous nature of this type of replication, followers will lag behind leader, and such system would tend to provide some weaker consistency models like eventual consistency, or they could provide session guarantees. Let's summarize trade-offs of asynchronous and synchronous followers. So, first one is consistency. With synchronous followers, all replicas are always consistent with each other. And with asynchronous replicas, we have a lag which leads to inconsistency. So definitely synchronous followers win here. Next one is durability. Again, with synchronous followers, we can be sure that acknowledged writes, they are stored on at least several other locations except the leader, and failure of one node certainly would not prevent data from being available. Next one is performance. Performance is better with asynchronous followers because it depends only on local processing of the leader. And the second one is availability. Availability is again better with asynchronous followers because now the availability of the system basically equals to the availability of leader, but not availability of every follower. So asynchronous followers wins the availability contest. But in fact, the choice between synchronous and asynchronous replication is not binary. In practice, most databases would allow to set this synchronous property not on a system level, but on each follower level. It means that we can configure which followers will be synchronous and which will be asynchronous. In that way, the system becomes very flexible. By choosing the number of synchronous and asynchronous followers, we can balance those trade-offs of durability, consistency, availability, and performance. Often it makes sense to have only single synchronous follower and the rest followers could be kept asynchronous. In that way, we can be sure that there is at least one node which stores the data after they were acknowledged. So it means that the data will be durable. And also there is one more node except the leader which we could use to make consistent reads. Additionally, it does not worsen too much performance and availability because it's just a single node except the leader which needs to be involved synchronously in the write process. There is a variation of this schema when we have multiple partitions and each partition has its own leader and its own followers. Despite that we have multiple leaders, in fact this schema remains a single leader schema because each piece of data belongs specifically to single partition which has only one leader. It means that each piece of data still can be written only on one node, and it means that there is a total order for this piece of data, to the updates to this piece of data, and that there can't be any conflicts. So overall, this schema provides almost all properties of conventional leader-follower replication schema with a single leader. So the edge cases are only related to some, for example, transactions which involve multiple partitions and so on. Partitions, or shards in some terminology, they are evenly distributed across multiple physical nodes, so that one physical node can contain both leaders and followers of different partitions. This approach allows horizontal scaling by distributing write load across multiple nodes, and also it reduces blast radius of single node outage, because only some partitions will be affected by this. The downside is that data changes across multiple partitions are not linearizable anymore, and we can't say which one was done earlier and which one was done later. It means that linearizability will degrade to sequential consistency. And also there could be some restrictions or difficulties in cross-boundaries transactions which involve multiple partitions. The most known examples of real systems which use that technology are Kafka and Elasticsearch. In Kafka terminology, nodes called brokers and shards are called partitions. In Elasticsearch, for example, we speak about nodes and shards. There is an interesting concept of local and remote write. Imagine we have a leader-follower system with leader located in Australia and client located in Brazil. And if client wants to make a write, it needs to send a request to remote leader. Obviously, it will not be very effective because of the network delay, because of the round trip, and it will be even more ineffective if client wants to make not a single write, but a series of writes, and probably heavy writes. This is how conventional and traditional leader-follower system works, and the writes are always have to be sent to remote leader node, despite the fact that we have another node nearer to the client, but this node is follower and thus it can't accept writes. All the examples shown in this video, they are specifically related to remote writes. But there is an alternative called local write. In case client needs to make series of writes to the data, leader could be temporarily transferred to the local node, which is very close to the client. Writes could be done on that node, and then a leader could be transferred back to its original location. So basically, in this approach, our system still remains single leader system. It's just that single leader is being transferred to another location temporarily. Let's see an example when leader located near one of the followers needs to make a series of heavy writes. Follower initiates leader switch over process, and after this process is completed, client can make series of writes locally on the nearest node. And after each write is completed, the acknowledgement is sent by a local node to the client, which works much faster. In this example, for simplicity, we assumed that the whole system has only one leader, but in fact, in general case, we could split the system into partitions or data pieces, and each piece of data could have its own leader. So basically, when we speak about switch over of the leader, we could just speak about switching over leader of specific partition of or a specific data piece to some other node, while all other leaders will remain on its places. Obvious advantages is that a series of writes by a single client can be done much faster when leader is transferred to a local node. But disadvantages are that this switchover process in fact is very costly and complex with a lot of side effects. And assume, for example, the case if multiple clients from different places of the world would constantly try to change the same piece of data, and in that case our system could be just paralyzed by a constant switch over of the leader. This technique is not very often used in practice, primarily because of this complexity of switch over process and the multiple pitfalls of it, and it provides more of theoretical interest. But it could be used in some systems, especially if the cost of this leader switchover would be less than cost of sending multiple heavy write requests to remote nodes. Similar technique is implemented in network file system version 4. It's called delegation there, and if client wants to modify a file, leadership over that file could be transferred temporarily or delegated to this client. And if in parallel other clients want to modify the same files, then server could revoke previously delegated leadership and reacquire the leadership of this file. This is described in more details in this RFC description. Another technique which is used sometimes is called cascading replication when we have several tiers of followers. The first tier get updates directly from the leader, and all subsequent tiers they get updates from followers of upper tiers. This approach can help scaling our system when there are hundreds of thousands of followers, and it would overload leader if a leader would have to send replication streams to every follower, and that way we can distribute load more evenly. Sometimes it can be used in multi-data center replication when there could be one follower in each data center which receives the updates directly from the leader and then fans out changes to other followers inside of this data center. The problem of this architecture is its operational complexity to maintain all of those paths of replication, and also in case some follower of upper tier breaks, then a replication stream could stop for all other followers in this branch. Also, the replication lag of the bottom tier followers could be significant. Such approach is supported by Oracle and PostgreSQL. Let's talk about discovery and routing in leader-follower schema. We know that client must send write requests to the leader, but how client would know who the leader is? So basically, we are saying that we need to have some knowledge, some topology map, which is constantly updated according to the actual situation. And depending on who stores and manages this topology map and routes the requests to proper nodes, we can have several different configurations of the system. First, what comes to mind is that the topology map can be stored and maintained on client side. In that case, client always keeps up-to-date information about who is currently the leader and about cluster structure. And when it sends write requests, it sends them to leader, and read requests it sends to either leader or to followers, depending on the application logic. Some examples of systems which work like that are MongoDB and Kafka. This schema is the simplest from server implementation point of view because it basically simply moves all logic related to routing on client side. Because client establishes connection directly with the needed node, the latency is low. Also, there is no need to any extra infrastructure components and costs associated with them. But its main benefit becomes its main drawback. Because all logic is moved on client side, it means that complexity of client side implementation is very high, because client has to manage this knowledge about who leader is. It should know about failover processes, which we will talk about later. Also, it leads to potential version compatibility problems between client and servers, because too much logic is placed on client side. In some circumstances, this could be considered like a security vulnerability, because the internal topology of the database system is exposed to client. To relieve clients from this burden, we could introduce additional component called router and place it in the middle. Now clients could send requests to this router, and the router will route them to the specific node. In that case, all the logic related to routing to the discovery will be placed inside of this router component. The examples of such approach are HA proxy and MySQL router. In this schema, a router handles the complexity related to discovery and routing, and because of the centralized logic, which is located on server side, it means that we have more granular control over it. And we can implement some very complex routing rules. And for example, they could depend on current system load, or we could orchestrate some complex transition processes and use router for that. Additionally, it allows to use connection pools between router and the actual database servers. And this could save us time on establishing network connection. The trade-offs of this approach is the costs associated with a single central router component. Additionally, it could be a point of failure. It introduces additional latency because of this additional network hop required for each request. And of course, it's an additional component which needs some maintenance. It needs some infrastructure and costs associated with it. To avoid additional component, we could use DNS, which is our existing infrastructure, which we anyway will have in any system. And in that case, we could have some additional component which monitors the system structure, topology, and configures DNS according to this topology. In this approach, though we have two kind of additional components, they are not really high loaded, because this component which monitors system changes and reconfigures DNS, it does not do a lot of work, because usually system reconfiguration does not happen often. And DNS also is not very high loaded because of DNS caches which client has, so client does not do DNS requests on every request to the database. An example is Microsoft SQL Server always on replication. It has a DNS name and virtual IP which always points to current leader of the cluster. The main advantage is that we don't need additional component which is high loaded and sits on critical path, and we have built-in caching. And in general, it simplifies client and server implementation. But it has negative sides as well. Because of the caching, the cluster topology updates are not propagated very fast. And also there is a question of choosing of time to live for DNS records and impossibility to implement some complex routing. Another interesting approach is to use nodes themselves to perform discovery and routing, because anyway nodes have this information already, and in this approach client would always send a request to any node, probably it could be the closest one, and the node internally it would know where to forward this request to be processed. This approach is chosen by Elasticsearch. Here we keep simplicity of a client. We can implement very complex routing on nodes if we want. We don't need to have some central component with additional costs, and it seems to be a very good approach. But there are also drawbacks, because this routing logic now is placed in the nodes itself. It makes nodes more complex. Also, we have this additional hop, because each request will come to the nearest node and then it will be sent to the proper node to handle this request. So it will be similar to router component. But of course it will not have extra cost associated with it, but the hop still remains. Also, it introduces a lot of inter-node traffic, which could make debug very hard. And in general, it could be hard to support and maintain. So far, we have seen 4 methods of discovery and routing, and there is no best or worst. Each method has its own benefits and trade-offs. So for each system which we design, we would need to choose the proper approach. Basically, in most practical applications, you would not have to choose this, because it will be chosen by the underlying technology. So if you choose some database, then basically you are bound to accept their method which they use, but it's good to understand it to know the limitations and benefits.